Thank you everyone for attending this important webinar in our series related to AI research. On behalf of Chicago State University and the team at our Center for Information Security Education Research, and also National Science Foundation as a funding agency for this project. We really would like to welcome Dr. Shuaibi, Muhammed Shuaibi, who is a research scientist at Meta. And we are really grateful for his acceptance to be our speaker for this series. That's Spring 2026 series. It's the very first webinar in this area. Dr. Shuaibi has a strong background in the area of chemistry, and at the same time, he is also a research scientist at the FAIR team at Meta. The way this will go, he will give his presentation for around 40 to 45 minutes. Then he will entertain a few questions, and then we'll conclude the session. This session will be recorded, and the floor is yours, Dr. Shuaibi.
Awesome. Thank you. Thank you, Musa. Hello, everyone. I'll try to keep this as high level as possible. Many engineering fields kind of do things numerically and computationally to simulate things rather than doing it in real life always. The second axis is models. There's a wide breadth of models. You're probably constantly hearing about them. There's kind of models in the machine learning, deep learning space. There's also generative models. You kind of see the stuff with OpenAI, the generative models, all the generative AI tools that are coming out, and you're probably seeing everywhere. There's a wide variety of different models we can kind of come up with. And lastly, there's lots of representations here. So you can have images as images for models, videos, text, audio, all sorts of things. And lastly is how do we actually use these models to address scientific problems? One, there's kind of hypothesis testing. I may be curious to say, how does this molecule behave in the human body? So I proposed a hypothesis. I want to use my model to kind of test that hypothesis and kind of publish that work to kind of study that specific problem. And similarly, there's kind of predictions and decision making. So there's large scale, hey, I may have a great model. I want to study all the possible protein structures related to, I don't know, some disease that may be significant. So you may run these models at high throughput to kind of study all that. And as far as what the applications may look like, there are too many to count. I think I threw a few here. You have the realm of astrophysics, you have weather forecasting, kind of molecular design, renewable energy, pharmaceuticals, drug discovery, electronics, microelectronics, things like that. Like the space is very large. Really, people can tackle anything that they're interested in. These days, really any domain of engineering, there's some application of AI just because of how versatile it is. And lastly, there's the axis of scale. So science discoveries happen at various scales. So at the very large scale, we're talking about weather forecasting. If you look at the far, do you guys see my cursor? Okay, at the far right, you have things like weather forecasting, you have astrophysics. These things are significantly large. Science there happens over maybe hours, days, not necessarily milliseconds. But then you also have things on the complete smaller end of the scale. So atomic structures. These things happen on picoseconds, femtoseconds, very tiny time scales. And the size of those things are extremely tiny. So you don't see an atom, but we know it's nanometers, significantly smaller. And this is most of the work I do on the day-to-day, and I'll talk a bit more about this, but just to give you a sense of the work I do is focused on one very small part of kind of a huge scale of different applications. So how does FAIR and the FAIR chemistry team and Meta kind of fit into all this? So for those not familiar, Meta is kind of obviously a social media giant, but we do have research organizations within the company. So FAIR is kind of our fundamental AI research org, and that's really blue sky research focused on AI. So researchers are free to kind of explore problems that are related to AI in a variety of applications. And one central theme is we're kind of committed to open and reproducible research. So a lot of the work we do within FAIR, you'll see the models are open source, the data is open source, the tools are open source, so we can kind of enable the community to use it and apply it to whatever application. And speaking of application, like Meta is not focused on science. Most of the folks in FAIR kind of work on language modeling. So like ChatGPT related things, models like that. We have Llama. You have vision models of how you can use vision models to kind of segment things. You also have language models of like, there's a big effort of translation. How do we have any language be translated seamlessly so anyone can kind of communicate across the world? And more, all of these kind of have this theme of open software libraries. There's hundreds of thousands of GitHub repositories and code out there, so people can kind of go out there and just download these models and play around with the tools. And for us, we're kind of the fair chemistry team. So we're fairly new. I think we were probably 5, 6 years old now. But our focus is how do we kind of use AI to apply it to chemistry and material science applications. So there are a variety of important challenges within tech and society for chemistry and materials problems. We don't have enough time to kind of go into all of them. So to give you a sense of what our team works on, we kind of work on a few domains. So we have catalysis, inorganic materials. I'll dive into these details a bit more if these terms aren't familiar. You have general molecules, molecular materials, things like that. Just so I can kind of walk you through the process of what this looks like and what discovery happens in one of these, I'm just going to focus on one for today's discussion, and then we can highlight a few at the end for the variety of applications. And the thing I'll highlight is catalysis. So at a high level, one of the big problems that we care about in the context of catalysis is obviously climate change. We know renewable energy, we know the energy requirements are kind of increasing. We want to shift to renewable energies, but there are a variety of problems that come with incorporating renewable energies. As we can see with kind of something like this, renewable energies currently exist, and the way they store the intermittency is like you may have batteries that kind of connect to your grid, or you may have light transportation, so like EV vehicles. But the one issue is we're not seeing renewable energy applied to a variety of other domains like heating, agriculture, shipping, AV. There's a whole variety of industries that aren't making use of renewable energies. And you can see that some of these have absolutely 0%, but most of these are kind of dominated by traditional energy fuels. And the issue here is most of these are often like high energy polluters. So a lot of these have some of the highest emissions coming from these variety industries. So the shift to renewable energy is particularly important for these domains, for these industries, because they are big contributors to kind of global emissions. And one way to do this is like, okay, why don't we just increase energy production? Like, let's get more renewable energy, like install more solar panels, install more wind turbines. Let's generate more renewables. That will solve the problem. And to give you a small taste, like we just take a random day in California, and this is kind of looking at the energy demand of California, and this is the current wind and solar supply of California. We can see that, okay, the naive solution is let's just scale everything up. Let's just install a bunch more. What happens is you run into the scenario where you start to have a lot more solar supply than you have demand. So the issue is during this period, for instance, you have high demand, but you don't have enough renewable energy to feed that. But in this instance, you have a lot of renewable energy, but you don't have enough demand to kind of fulfill that. You can imagine that during the day when the sun is up, you have energy, but we don't need that much energy at that time. And similarly, at nighttime, the sun is down, maybe the wind is blowing less, the demand is still high, but you don't have that renewable energy to supply to feed into that. So the question here is, how do we kind of make use of the high energy supply during peak times and distribute it to times of high demand? And that's really the catalysis problem, is how do we incorporate catalysis, feed in the renewable energies with some of the renewable energy resources to kind of store that energy so we can use it at a later time for these different applications. And this is really the reason these industries haven't made use of renewable as much, is because it's too intermittent. They need a reliable source of energy. And one way to do that is, okay, let's capture that energy, store it, and then use it later when we actually need it. So now to give you an example of how that may look like is during excess generation, we may have some source of electricity. We'll use that electricity and we'll take a water molecule. And the idea here is we can break this water molecule with this electricity and you have hydrogen and oxygen. And what we could do here is we can store that hydrogen. We can store this hydrogen gas. And then during times of excess demand where we need more demand, but we don't have enough generation, we can take hydrogen, feed it with oxygen, and then we can run this reaction and produce electricity. And this is what we refer to as a fuel cell. And the one key ingredient to make this happen is a catalyst. So for those not familiar, what a catalyst is by definition is a material used to increase the rate of a reaction without being consumed in the process. So this reaction right here, like producing electricity, does not happen if you just put hydrogen and oxygen together. You sort of need this catalyst material to enable this reaction to allow electricity to be generated. So now the big question is, okay, how do we discover new catalysts? Like we know catalysis is an important problem. We need to find new catalysts. And the big question is, how do we actually study that? And traditionally, this has happened in the lab. Someone will propose a material, they'll go in the lab, they'll spend hours studying it, and they kind of figure out if it's good or not. But one thing we've been doing is we can study this kind of at the atomic scale. And to give you a sense of what that looks like, I'm going to give you an example of a Toyota Mirai. So this is a fuel cell car, but made by Toyota. And the idea there is you can have hydrogen and oxygen, and it produces electricity, and that electricity is what makes the car move. So how exactly does that work? Like let's take a closer look. So inside the car, there is a fuel cell. So like some sort of battery, like you can think of it as a battery, but it's a fuel cell. And this is kind of the source of electricity. And let's take one step closer and like this is the actual oh, I lost something on my screen. The catalyst material happens here. So you have this interface, and a catalyst is necessary. Like these metal plates, the cathode and the anode are catalyst materials. And this is what's key to kind of make this car run. So let's kind of walk through that example. So you have a reaction that happens in this car. So you say you have oxygen plus 4 hydrogen atoms and you produce water. So what does that actually look like? So this is the catalyst material. This is like a metal plate inside the car. You have oxygen intake. Oxygen is coming into the car. And just for vocabulary, this is considered an adsorbate. So any sort of molecule we refer to as adsorbate, and the metal surface we refer to as a catalyst. Oh, it started. It's fine. Anyhow, so you can see that this oxygen molecule will come to the surface. Let's see if I can get it to restart. Okay, so you'll have this oxygen molecule. It will arrive to the surface, and then we call that binding to the surface, like sticking to the surface. Once the adsorbate kind of gets to the surface, you have these hydrogen atoms that come to that molecule and kind of take it off that surface. So now you've produced what you started off as O2, you now have 2 water molecules. And this is kind of the high level overview of what we're studying and what we're looking at when we kind of discover new catalyst materials. We want this kind of Goldilocks effect. We don't want something to stick too strongly because you can imagine that if you have oxygen come to the surface and it's stuck there strongly, nothing is going to kind of be able to remove it. So hydrogen won't be able to come and remove it, and you just kind of saturate your surface with just oxygen molecules. Similarly, if it's too weak, nothing will bind to that surface. So nothing is going to stick to there. No chemistry is going to happen. You're not going to study any reactions. What we want is kind of this just right equilibrium where you have things that bind, hydrogen comes, pulls them off, and you have this kind of back and forth that enables this chemistry and makes this catalyst work. So what we do is kind of study this on a computational level. So I talked about traditionally people go to a lab studying it experimentally. I'm not going to get into the details of what the quantum chemistry here is and the details of how this works, but at a very high level, just imagine we have a simulation tool that traditionally you can feed in and you can input an atom structure and we're able to study properties from it. And this is considered density functional theory. I'll refer to it as DFT throughout the talk. One thing to note about this traditional computational tool is it scales extremely poorly. So as we go to bigger atoms, it takes significantly longer to run. Kind of the DOE's kind of national lab supercomputers these days are primarily occupied by running simulations of this kind. So it's extremely expensive, extremely costly. And if you were to imagine studying things that we are unable to study with DFT are things like nanoparticles or proteins. These are things in the biological system that are extremely important to study, but we're unable to because this scales so poorly and it's going to take years to actually run. So when we think about kind of accelerating innovation and how do we actually use AI to push chemistry and materials forward, we think about it on kind of four axes. One is you have these computational tools. You have the traditional computational resources that we are building AI models to kind of replace. And now, once you have AI models, we want to see this in action. You want to take this AI model, compare it to experimental results. Can you actually make this discovery loop happen? And what we think about accelerating innovation is we kind of want to do this in an open nature. Like if only one person is generating data and not sharing it to the community, it's not beneficial to kind of push the field forward. Like this is a very early stage research in the sense that we need a lot of ideas, we need a lot of minds thinking about it, and how do we actually scale it together, and how do we focus on very specific challenges to make this reasonable. And we've started two sort of pilots to do this, so kind of doing this full workflow. One is called the Open Catalyst Project, and this is focused on catalyst discovery and what I'll talk about today. Another one is kind of Open DAC. So this is direct air capture of how do we kind of capture harmful pollutants like CO2 from the atmosphere and convert it to something good. But today I'll focus on the Open Catalyst Project. So at a high level, related to catalysis, the Open Catalyst Project is how do we use AI to find new catalyst materials to address climate change? I talked to you about what an adsorbate is, the molecule, and the catalyst surface. The problem we're really studying here is we will start with some initial structure. So we'll have some molecule on some catalyst material, and this state is often high in energy. And the problem is, how do we find the ideal state for this molecule? We run these computational tools like DFT, and you can see that it studies how the molecule behaves on the surface. So you can see that this is the result of that simulation. You can see that CO actually moving and laying down on this metal surface because it's now in an ideal scenario, what we refer to as a relaxed state, low energy state. So this is where it wants to be. And the key thing here is this low energy state is what we can use to study the properties and say if this catalyst is good or not. Now, the issue is DFT here is extremely slow. This simple simulation takes around 24 hours. And if you were to think about screening the entire material space, you have billions and tens of billions of different possibilities. And that's just impossible to actually screen in our lifetime. So the thing we're trying to do here is instead of using density functional theory, where the input is an atomic structure and the output is energy and forces, this is what we use to simulate the reaction. Can we replace it with machine learning models? And the idea here is machine learning models can be like orders of magnitude faster. So we can run things 10,000 times faster, oftentimes even 100,000 times faster. And this gets you to the point of, okay, now that we have really fast models, can we study the science much more effectively? And of course, to build kind of these big machine learning models, you need a tremendous amount of data. I'm not going to go through all of these, but this is to give you a sense of you need lots of training data to kind of do this. And what we do here is we use that computational tool I talked about, the DFT. We run that on kind of Meta has tons of servers when they're not kind of running ads for your platforms, we can use their idle capacity to kind of generate training data. So here we've generated significant amounts of training data across different domains. And this data is kind of key to building these models and studying that reaction. So to give you a sense of what this actually looks like is this is maybe an input structure to our model or input structure to DFT is you have 3D atomic positions and you have atomic numbers. Here I'm just modeling an example of the catalyst surface. So you have this catalyst surface, you have some molecule on the top here. The output is energy and 3D atomic forces. So you'll have a single energy value for this whole system, but you'll also have forces. You can see these arrows correspond to the force exerted on each of these atoms. And knowing these two can enable kind of a lot of the scientific discovery and screening that I've been talking about. Now, on the model front, how we do this is we use something called graph neural networks. So graph neural networks are just another flavor of machine learning models. I'm not going to dive into it in depth, but here just to give you a quick taste of what that looks like is graph neural networks are very analogous. The input structure to graph neural networks are very analogous to how atoms look like. So what we do here is this is what the structure looks like. We'll convert it into nodes. So here, a node corresponds to an atom. And the other thing graph neural networks needs are edges. So this is what we consider neighbors. So I need to know that this atom exists, but I also need to know that what's the distance between me, myself, and the nearest atom, and so on and so on. And the idea here is with just these two, knowing the nodes and the edges, you can kind of build a model around how we can communicate information between different nodes, and we can kind of use this representation to kind of make predictions for energy and forces. And one thing that we did with kind of building these models is we wanted to kind of enable the community to come up with better models. So what we did is kind of start these open leaderboards and AI ML community challenges where we release the data and we have the community, the ML field kind of come up with better models. So like people can go to these websites and make their submissions for their predictions, and we'll evaluate for them and kind of have a leaderboard to track kind of the progress in the space. To give you a sense of what that looks like is like, this is one of the kind of state-of-the-art models probably 2 years ago, but this is kind of the relaxation we talked about. So I showed you how you start off with some initial high energy state, and then over the course of the simulation, you arrive to this lower energy state. So on the right, you kind of see how the atom begins and how the atom ends in kind of this lower, more favorable position. And the idea here is the top is the ML model, and the bottom is kind of the ground truth computational tool. And what we can see here is that they get really close to, you can see that the energy values are very comparable. And what's amazing here is this took almost over a day to compute, while this took like 5 seconds. And it's things like this that we can use these models to then run screening campaigns at a much larger scale. So that's exactly what we did. So what we did here is we partnered with kind of industries and other academic labs. So this is the University of Toronto, and this is a startup in the Netherlands, VS Particle. And what they have is these automated robots to do chemical synthesis. So you can see this robot moving, and it's kind of mixing things together, and it's kind of running these reactions. Similarly here, this is what we call like a printer, where it shoots the materials onto the surface, and that's kind of the catalyst surface that we're going to be using to study. So we partnered with both of these to kind of generate a bunch of catalyst materials that we wanted to screen, and we studied this fuel cell problem that we talked about. We refer to this as the hydrogen evolution reaction, and that's where we take water plus electricity and you produce hydrogen and oxygen. And at a high level, we're seeing strong correlation. And I think that one thing to note here is experimental to computational connections aren't going to be perfect. So you can look at this and see this is not a perfect correlation, but the idea here is we don't necessarily care for perfect correlation. We just want to capture trends. We want to say something here is better than something here, as opposed to what is the exact value of this. And with this model, we can use it to like run a larger inference campaign and kind of study materials. And the unique thing here is like we're able to reproduce materials in the literature that are known to be great for this chemistry just through AI tools that are orders of magnitude faster. So that's kind of an overview of the catalysis. So that's the state of fair chemistry. So much of this work started in 2020 to 2022. So the focus there was catalysis. And we generated a lot of training data. We generated a lot of models. We collaborated with experimentalists to kind of generate real data to compare against. But we wanted to shift to exploring other applications. I told you that there's well beyond, there's several applications that we can study. One of them is molecules. So drug discovery, studying proteins. Honestly, the space of molecule applications is numerous. So medicine, batteries, manufacturing, climate. There are a variety of applications where studying molecules is very important. So similar here is we kind of follow the same cookbook recipe where we have an application we care about. There is significant lack of data in the community, so we can generate computational data through the tools I talked about, and then we can kind of build out these models and use these models for real science. Similarly, we have like the open molecular crystals data set. So this is similar to the molecules data set, but instead of just a singular molecule is how can you pack multiple molecules in a cell to kind of form a crystal? And this is important in electronics, important in pharmaceuticals. So the idea here is that one catalyst data set isn't sufficient. We have to kind of generate these different data sets for different applications in order to study these different tools. So one thing that is relevant to Meta, and I think I often get this question of why is Meta working on science? So one aspect is we have the freedom to explore kind of big scientific AI problems. Another one is there are internal applications. So when we started this project, we weren't working on this. We were focused on catalysis. But I think over several years of working on this problem, internal product teams came to us and they're like, okay, hey, the glasses you wear on your head are a materials discovery problem. So the glasses I'm talking about for Meta are kind of the AR glasses. So you've probably seen the Ray-Bans, you've probably heard of the VR headsets, but specifically say the AR glasses, for instance, to be able to kind of get high resolution, especially if you want to see displays inside your glasses, you need to have high resolution. You need to be able to have a high field of view. All of these are materials discovery problem because depending on the type of material you're using in the glass, that's kind of critical to kind of studying these properties. So that's something we've been working on in addition to all the open science stuff is these internal applications of these models are working really well for catalysis for molecules, but they're also working well for internal applications. And we can see things like this was kind of announced, I think probably last year, the Orion headset, where this is kind of the future vision of the AR headsets. And this is a materials like here they use silicon carbide, which is what's the material inside the lens. And at the end of the day, this is a materials discovery problem. So alongside the open science we're doing, we have internal applications where these models, the same models that I talked about earlier, are also used for like real products that are happening inside the company. So over the past several years, we had a variety of applications. We had like the direct air capture, materials, molecules, and molecular crystals. And then one question we started to ask ourselves is this recipe is kind of boring in the sense of, okay, I have a new application, I generate data for that application, I train a model, and that model works just for molecules, or that molecule works just for materials. One thing we started to ask ourselves is, can we combine these models? So one thing that is we've been hearing a lot in the field is the idea of this universal model or this foundation model where we need to move away from just having a model that only works for one thing. Can we kind of build a model that is universal for chemistry applications, for material science applications? And that's what we kind of set out to do last year, where we have these big, incredibly large data sets, and can we just train a single model across all the data that we have and make it work for anything? So that way, if I wanted to study something for chemistry, I can use the same model. But if someone in the biospace wanted to study protein design, they can use the same model. And it's really enabling the community because oftentimes the community is stuck because their specific application isn't covered by some model. So the idea here is we have what we refer to as the universal model for atoms. We call this UMA. I'm not going to go into these details, but the idea is we have all these data sets, we train them together in this new architecture, and we have a single model that can kind of run a variety of computational screening kind of simulations. So the things I showed you with the catalysis are often relaxations, but if I wanted to study how a protein behaves inside your inside your body, sorry, I need to run this model for incredibly long time scales. So something like molecular dynamics are tools you would use with this model. And we're working on this being also an educational tool. So I think a lot of people when they study chemistry and they study materials or whatever the application, many of these things aren't intuitive of how bonds form, how things react, ionic bonds, covalent bonds. One thing that we're working on now is kind of building this demo, this kind of educational tool for the community to use. One, they can use it to kind of study specific scientific problems they care about, or two, they can use it just to kind of as an aid inside the classroom. And that's something we're gonna pilot very soon. The demo I'm gonna show you now is not. We're working on a newer demo that we're hoping to refine for educational purposes, but we released this demo alongside the release of the model just for people to play around with. And you guys see the new tab, correct? Okay, cool. So the idea here is, yeah, obviously there's lots of descriptions and details that people can read and understand the model better. But at the end of the day, people can come here and upload a structure they care about, a molecule they care about, and they can kind of simulate how it behaves or how it reacts. So for instance, let's see if this works live. If I click this simple, we'll refer to as a transition metal complex. And the idea here is you have a metal atom in the middle, and then you have these organic species surrounding it. And this is kind of important to study. So this is the structure I wanted to study. And the idea here is I can tell it to, I want to simulate this for various time scales. And then when you can run these simulations, the results kind of show up here. And then you can see that using our models, our trained models, this is kind of how you can expect this molecule to behave. You can see how like the hydrogens are oscillating around the carbons. This one's not particularly interesting because it is a stable species, but the idea here is you can imagine people putting up various reactive species and you can simulate how that behaves. And this is kind of, this one you can access today, this one at the following link, and we can probably share that. But the idea is we're working on a second version of this, which is more educational focus and more kind of more simplified for someone who may not know chemistry at all or materials at all to kind of use this as a tool in your classic chemistry classes, in your honestly on any scale between high school to even grad school. We've seen this incredibly useful. So with all this, kind of many of the like the UMA release was kind of the biggest thing we had last year, and what we're seeing already is what's central to kind of pushing the field forward for science is making these tools accessible. So like open models and open data sets is something that I continue to emphasize on, and that's because our team is only a dozen people. We can't study all the scientific problems in the community. No one really can. So I think the idea is, can we just give the community the tools to do that and let them go free and kind of study whatever chemistries they care about? And we released this model mid last year, and we've already seen over dozens of applications and publications of people using this model directly to study various problems that we've never even heard of, but is exciting for their specific application. So I'm not going to go through these in details, but I think it's just to emphasize that it's incredible to see how fast people are quick to adopt these tools and apply it to real scientific applications. So in summary, several points is one is AI for science isn't new. Science for AI isn't new. It is an incredibly rich problem space that has kind of various applications. I think one thing that you probably often hear in the news these days is just anything related to ChatGPT and the generative models. Like when we think of AI, that's probably the first thing you think about, and less so the cooler applications to science and engineering. And it is incredibly rich. There's a variety of application that anything you can think of, or honestly anything for even some of your guys, some of the work going on your end, can be relevant, and someone's probably exploring something in that space. Um, for my particular application, we study things at the atomic scale. So that's what we're kind of building models to study things at the atomic scale. But that's not to say that AI for science is limited to that. But we see, I focus on the atomic scale, but I showed you the figure of the various length and time scales, and people are working on building tools for different applications there as well. And I think really the main thing I want to focus on is kind of the open nature of data sets and models. And I think that is central to pushing the field forward. Like AI for science isn't new, but it's still in its infancy, where this is all still new tools, new things are coming out every other day. And the best way to kind of push this forward and kind of see groundbreaking changes is kind of through these open data sets and open models. I go back to that very first Nobel Prize in chemistry for protein structure. The reason that was so successful is there was an open data set of experimental structures that people can go and build models for. So without that rich experimental data and rich open data, people couldn't have kind of gone after these grand problems within the AI space. And obviously, this work isn't just entirely myself. This is kind of the full Meta team. We had numerous collaborations, especially when it comes to building data sets. Our team aren't particularly experts in all the different domains. So when we're not an expert in a domain, we kind of go seek the leading experts in the community to build that for honestly not just ourselves, for the community to release. And that's all I have. Thank you.
Thank you so much,
So,
Muhammad. I really appreciate it.
yeah,
Thank
sorry if
you
that was
for.
too much in detail, but there's plenty of time for questions, so I'm happy to
No,
entertain.
no, thank you so much. I really appreciate it. I like the structure and how it really shows how AI is impacting chemistry. Before I know I'm not the chemist, maybe I'm not the last. I'm the last one to ask questions here, but I'll ask anybody here in the audience has any question. Mohammed, this is before I get first of all, thank you so much for the presentation and what you shared, like you shared with us today. First of all, please, if you could share with us the link so related to the tools that you showed, because I want to share them with the faculty from the chemistry department and biology department. Maybe they see how to benefit from. I
Yep.
really appreciate it if you can share it with us, so we can send it to them. My question is. How, again, the fact, again, I'm not a chemist, but I see a good connection with what you're sharing with in my field, electrical engineering. I can see
Mhm.
some of these tools can be utilized one way or another. How do you see this being generalized into other STEM areas or other areas of science?
Yeah, so I'll speak to the atomistic research that we're particularly doing, and one thing we're doing is like at the end of the day, and this is kind of feedback from the community. I've chatted with several industries where they're using these models for like say chip manufacturing. So kind of how do we like silicon wafers and how do we actually do that and etch things into chips? One thing, it used to be kind of a physical process where you actually are chipping wafers, but now it's sort of a reactive process. So what we're seeing within that community is people studying kind of the catalyst problem of what is reactive enough on these silicon chips so we can kind of build these electrical components on their scale. So that's something that I've seen within the atomistic world. We've also seen another super popular thing these days is kind of semiconductors and superconductors. So the discovery of those has been there's particularly a surge these days. Like we've seen.
Right now, they're talking about AI for.
Please go ahead, Mohammed.
Sorry. Yeah. Sorry. I'll finish my thought. Yeah. So, like, we've seen a lot of work of excitement around finding new semiconductor and superconductor materials. So, I think one problem is like a lot of the engineering components are sort of secondhand to the discovery problem. So like I may find a material that is good for the AR glasses, right? But just because I find it in the lab doesn't mean the engineering works out to scale it and produce it and put it in these components. There's a lot of varieties. So we're sort of in the infancy where we're still trying to find the initial ignite where like, hey, can we find these initial materials that look promising, and then can we pass them to people to kind of scale and more rigorously test this on the engineering front? So that's what we're seeing on the atomistic level. On the kind of a bit more macro level, like a bit higher than that, like we've seen people build models. Like AI tools in general are kind of very versatile. So like yeah, without knowing the details of the research going on, like I think robotics is a huge one that's happening. Embodiment AI is how do we kind of build these AI robotic platforms. So um, one thing I showed here is this sort of is a robotics problem in the sense of there's AI, like you have all these sensors and mechanisms, but how do we actually build the AI tools to properly operate this? So this one is in a specific like laboratory setting, but we're seeing applications to like you've probably seen the humanoids of people. How do we build robotics at a bigger scale of having a humanoid in your house assist you? That's not really a product problem right now. I think it's really a research problem of how do we actually go after it. But I think I don't know, there's a wide range of applications, but at least at that atomistic front, we're seeing like semiconductor, superconductor, microelectronics have been really exciting as far as using these models for that discovery.
Thank you, Mohammed.
And- Sorry, and just to be clear, I think like it is so in it's very much in its infancy that like there's dozens of startups doing it and like there's no big success story. Like I don't think like you haven't heard anything yet because people are still actively working on this and no one's found like a new semiconductor that's exciting for applications yet. That's why it's like a very ongoing field of research. Sorry, go ahead.
Oh, thank you. I see there was a question by Korean. You had a question? Oh, okay. There's a question here about are there conversations about energy usage pertinent to AI modeling? I know it's a general question, but if you can
No, no,
shed
no.
some
I
light.
think it's a great question because there's often criticism of some of these models are extremely expensive to train. So like you'll need, yeah, I can't even quote the numbers, but like there is a lot of discussion around all these big tech companies are training very large AI models and it needs incredible amounts of compute. And you've probably seen the news, people are constantly building data centers and kind of these, you need these to house the GPUs to train these models. So at least I'll speak on the meta side at least. Like one thing that we've been doing as of recently, I don't know how recently, but like it's sort of all our electricity is shifted to 100% green. So to sort of offset, like yes, we're producing a lot, but I think the idea is we are doing so through green energy. So I don't think that's the future. I think people need to think more about how do we make models more efficient so we don't have to use those resources. But that is very much an active discussion, at least in the broader sense within the company. To be fair, for like the models we build, I don't think are anywhere on the scale of like stuff like ChatGPT and that. So I think that's something we don't think too much into, but it is a great question and something that at least our company is actively thinking about in terms of how do we get green energy to enable these data centers.
Thank you so much.
Thank you. Michelle, you had a question?
That
You
was
had
my
a question.
question.
Okay, thank you. One more question about there's I don't know Shamuel or Shamuel can share his question, but I mean, how many models do you have and plan to release? Will it be one single platform? Have you mapped your model to the applications in a structured manner? I know there are many
Yeah.
questions, but
Yeah. No, I think that's a good question. I'll start with the models. So over the past 5 years, we worked on five main applications like molecules, materials discovery, catalysis. We have these molecular crystals and like direct air capture. Um, so we have five extremely large data sets. All of these data sets are open source. People can use them right now today. To like if you were interested in training new models, you can take that data and train it today. On the model front, we have models within each of these applications. But one thing that we've been doing is that's sort of outdated. Like I don't encourage someone to go use a catalyst specific model. Like this, what we released here, this UMA model, we released this mid last year. And I think this is still gaining popularity and people becoming more aware of it. Is like it's centralized. Like any application, like so long you're interested in atomistic research, any application within molecules, the five I listed before, is covered by this single model. So this model is open access. Like you can go actually download it today. Um, and like yeah, we have like I can share stuff. Maybe I'll share. I don't see a link. I don't think there's a chat here I can drop links to. But maybe I'll share it with Musa over email. But I can share the links that if anyone's interested, like this model is publicly accessible. If I was interested in doing any atomistic research, this is the place to start. So that is available today. I'm thinking of the second part of that question. Maybe Musa, can you remind me?
let me go back. Have you mapped your models with the
Yeah.
applications in the structured manner?
Yes. Yeah, so that's a great question, and I think it's a difficult problem. So I talked about these five applications. What we really care about is you don't want to just take a model, release it, and say the end, because like people still want to see, hey, okay, that's cool, you have a model for your data, but can you go do real science with it? Can you connect it to experimental work and show results that are consistent? So to date, we've only focused on catalysis. And the reason we haven't tackled everything yet is it's an extremely slow process. So the catalysis effort took almost 3 years of going back and forth with experimentalists and getting the data. And this has been extremely challenging because, as you can imagine, experiments aren't easy. Just because I mix two materials together does not mean it's going to come out exactly how I expect. So there was lots of challenges with studying that problem. So this was sort of the case study of let's try this. How do we do this? Lately, we've been interested in the molecule space just because this community is extremely large and people care about like drug discovery and studying biological applications. This one is something we're interested in. But I think it is an ongoing problem. I think one thing that this space lacks is very structured experimental data. That way, like the models are structured, our data is structured, but to have structured experimental data, that way we can connect that gap, is really critical to enabling the space. So a lot of my research is kind of on the computational front, but this is kind of a call to action within the community of we also need experimental data to make this kind of to close the loop on this whole discovery process. And that's something we've been chatting with collaborators and trying to make happen. But it's a very good question that it is a limiting thing within the field and something people are aware of and kind of working towards. And I go back to the DeepMind Nobel Prize award. Like that one was successful. People were able to close that loop because you had great experimental data. You had an institution, a nonprofit institution, that every year would like spend their time to run these experiments so people can study it computationally. And I think that's generally lacking across the other domains.
Thank you, Muhammad. I think I have 3, 4 questions. Let's try to
Yep,
go
sorry.
over quickly. How often are errors or hallucination when testing? And how do you determine if the AI is going in the right direction?
Yeah. No, that's a good question. I think so for now, the way we quantify errors is just these models are predicting the energy and the forces. So what we've been quantifying is like what's the error on your energy, what's the error on your forces. As far as where this question becomes important is if I start to screen millions of candidates, these errors may compound. And the idea is I may study millions of candidates, and the model may propose something that it thinks it's good, but it actually isn't good. So that is something that is a very relevant question. I don't think we have we don't quantify that now, but I think the way we think about it as less risky in our sense is if I'm studying hundreds of materials, and you give me a few false positives, it's not doing much harm. Like maybe I wasted experimental time testing it, but like hallucinations maybe in other applications are worse. So like for instance, the medical field, if I have a chat GPT medical assistant that told me to take morphine because I had a headache, that doesn't sound good. Like I think that's going to cause some issues. There's a hallucination on that front. So I think for us, it definitely happens, but I think the repercussions are significantly less because we are at the end of the day testing it experimentally in a closed environment.
Okay, thank you. With the increasing usage and the potential of AI in scientific discovery, how will the role of the PhD in science change? And what are your thoughts on this?
Yeah, that's a great question. I started my PhD not wanting to not even aware of AI's popularity in my space. So I did a PhD in chemical engineering. I wanted to do just traditional process optimization. So how do we take big plants? How do we optimize flow rates, things like that. But I think me entering this space, AI was taking off. We can see applications to AI, and there was a single professor at my university that was exploring that space. So he was working on the intersection of AI applications to chemical engineering, to studying chemistry. So that was sort of kind of the gamble I took of like, let's try something new and go with it and see where it goes. So I think it's been 5, 6 years since I've gotten my PhD, so like a lot has changed. So I think nowadays almost like a lot of the engineering programs have AI in their curriculum. And I think one thing that I encourage is like even if it doesn't, I encourage any PhD student or people kind of pursuing higher education is at least familiarize yourself with the language, with the vocabulary, with what AI is doing. I think these days we're seeing tools so advanced that you need to know little programming experience, and you can kind of work with these AI tools to kind of build what you care about. So for folks maybe on this call or in the department that are tackling scientific or engineering problems, but are maybe hesitant because they're not super focused on programming, there's lots of tools that are coming out where you can ask the AI agent to write you the code to study the problem, and they've been working phenomenally. Like, I think as someone who studied that stuff, we're using it quite regularly. So I think the PhD role broadly within the scientific domain, we're seeing a lot more adoption of AI. I think the tools there are becoming very common, very important to accelerating scientific discovery. So I think we're just going to see more adoption over the next coming years of PhDs with AI experience. And if that program doesn't exist for you, I think that's something people should do.
Thank you, Muhammad. There's a very interesting question by Gerard. I'm going to leave it for you to say it instead of me saying it. Do you mind doing that, Gerard?
Yeah, that's fine. Muhammad, did you say that the catalyst increases the rate of reaction without consuming the catalyst?
Yes.
So,
Yeah. So the
so,
idea, go ahead.
go ahead. So the catalyst doesn't undergo destruction after it does
Yeah.
the.
Exactly. So yeah, the great question. Like the idea, the reason catalysts are so important and so valuable is, say we're looking at this image, you have this C3H8 molecule. On its own, it's not reactive. It's not going to convert to anything else. It's happy in its current state. It is comfortable. It's energetically stable. But the idea is, what happens is you arrive on this catalyst surface. Okay, you are not reacting with the catalyst. You, like, platinum is not connecting to the molecule. You are not pulling platinum off, nothing. So that's the nature of catalysis, where what it's doing is, what happens here is, obviously there's electrons flowing around everywhere here. The idea is this molecule lands on this platinum surface, but the way metals behave and how the electrons localize and spread around makes it so that when this molecule lands on the surface, imagine that someone is standing next to me and I'm that molecule. All they're doing is pulling my arm. Both of us are independent entities, but the nature of someone pulling my arm maybe makes it easier for me to grab someone. Like, my left hand can do something else. Like, I can go grab on, and say something else stronger comes on the left side, pulls me away, and then the role of the guy on the right was solely to hold me in place a bit so someone else can come and take me away. So, like, that's I don't know if that analogy made sense, but the idea there is, this catalyst is not consumed, and it is serving as a role to kind of play around with the electronic structure of the molecules and make them more or less reactive. That way you can break off and go do something else. So, like in this case, for instance, what's happening here is this molecule landed on this hydrogen, and then it sort of broke up. Like, you have a water molecule that fell off and then a different molecule that fell off. Does that make sense?
That makes a lot of sense.
Thank you, Gerard. Could you please share what you were sharing about the weather forecasting?
Oh man. So I'm a weather fanatic, man. I watch the Weather Channel like all day, right? And it's interesting how they're using more and more AI models now for weather predictions. And there was a time when they were adverse to using AI,
Yeah.
but
Yeah.
now they realize that some of the AI models are just superior.
Absolutely.
You know,
Absolutely.
they can track storms from Japan. You know, they don't just know that the polar vortex is going to occur and affect, but they know the capacity of how strong that vortex might be. I mean, it's quite incredible, and you know, it's saving lives too.
Yeah.
AI
Yeah.
models and weather are saving lives.
No, absolutely, exactly. So like this, what I'm showing here isn't our work. This is work from DeepMind. They put out a big paper last week on like weather forecasting, and this tool you can go to it now. It's like if you just Google DeepMind Weather Lab, like this is real-time weather forecasting of storms happening across the world. So it's like super exciting to see tools like this happening and coming out and kind of really making a difference. Like not like you, I like the point you made. Like not everything is discovery. Like I don't need to find a new material. This one is saving lives by giving people better heads up of dangerous, I don't know, storms, climates, whatever the case may be.
Yeah,
Okay.
yeah. I had one other thing to ask too. Um, so I'm in the humanities, principal preparation, in the Masters of Education department
Mhm.
at Chicago State. And I think that I may want to use some of your concepts today in creating an AI model. And I'm sure uh, Dr. Ayash can assist me with this. Create an AI model in the humanities that is outside of science but still incorporates it. That AI model I think I'd like to develop is for my principal preparation candidates. My students are, most of them have bachelor's and master's degrees. They want to be
Mhm.
principals in K through 12 schools. But
Right.
here's the thing, the easiest institutions to steal funds from are public schools in the United States.
Mhm.
And I want to create like a catalyst of ethics. Of course, it's assumed that a school leader will not take funds from the school corporation, right? That's the assumption, right? That they have high ethics. But I think an AI model could be created for principal preparation candidates not to steal funds by adding an the energy of stealing a fund or being ethical versus the risk versus the consequence, because so it never fails. I mean, you can google like principal or superintendent or school board theft, and it just keeps happening.
Yeah.
The kickback scheme, right? These people actually think they're gonna get away with this stuff. And I'd love to create an AI model for my classroom that says, look, the right high ethical thing to do is to not steal, but we're going to let AI show you 1,000 ways in
Yeah,
which you're
yeah.
going to get caught.
No, no, that sounds like a fun one. Like it's definitely doable. It's definitely doable.
Thank you, Gerard. Thank you. This is now we are at 12:02 here in Chicago. Thank you, Muhammad, for your time. I really enjoyed your presentation. I'm sure everybody here did the same way. Again, we appreciate your time and looking forward to meeting you in the future.
Yeah. Thank you guys. Have a good one.
You take care.
Enjoy the cold.
Thank you. Enjoy the nice weather.
Thank you. Bye.